Recording in progress.
Yeah. So again, for number one, make sure you state the units, the time frame, and of course the value that it equals. Then for part B is asking to actually state the t prime of 8. Now here's the problem. I don't have the equation, so I don't have a derivative to take, right? But what you can do, I didn't really talk about this, so I was hoping maybe you guys could figure it out. But what you need to do is you need to find values close to 8. So 6 and 10, are 6 and 10 symmetric about 8? Yeah, so you have to find things that are symmetric about 8 and find out if things are close. Because the hope is that you're plot these points, right? I mean, so the curve does this, right? But if you look right in between, the hope is that the tangent line and the secant line are almost parallel. That they're roughly the same. That's the hope. So that's why you just look at 10 and 6 and take that slope, which should be 3. And then again, to explain it, you're explaining that it's the instantaneous rate of change. So at the moment that you're at 8 hours, this is how the temperature's increasing by this much. You want to say it like that. So yeah, it's increasing by that much at that moment. At 8 hours, so the time, the units, and what's happening. Right? Those are 3. So what, when, and units. That's what we need. For number 5 is asking you to determine this differential x equals 1, x equals 3. So you could use shortcut rules. You know, I said so. So derivative x plus 1 is 1. Derivative 1 over x is negative 1 over x squared. The derivative 4 minus x squared is negative 2x. Then plug in the boundaries. If you plug in 1 to the first and second equations, are they the same? Let's find out. They are not. So we're not differential at 1. And then for the second and third equations, let's do those derivatives. Compare when you plug in 3. Also, they are not, because they're 2 different values. So you got to look at the left and right hand derivatives if they're not the same. Actually, take it back. At x equals 3, it's just not continuous. So forget about it. So check for continuity first. So when I checked for continuity for the first, second equations, actually that did work, but the differentiability was not there when I did the shortcut rules. For at x equals 3, I didn't even waste. We don't even have to check the differentiability part. It's not continuous, so forget about it. It's done. Just can't do it. So hopefully that makes sense. And for 6, ooh, I love these problems. Okay. Did we have this in our last test? We did, yeah. And they'll probably back in the final exam because I love this problem. It's just a good review. Dave too loves it too. Yeah, you're forcing the issue of continuity, but I think we're also forcing the issue of differentiability as well. So it's more than just that, more just continuity. So you plug in 1, you get 2 for the first equation, you get a plus b for the second equation. So a plus b equals 2. But that's not enough because you have 2 unknowns, but one equation, right? Then you got to check the differentiability part. Again, use shortcut rules. Negative 1 is the slope for the first equation. 2ax plus b is a derivative of the second equation. Set those equal to each other when you plug in 1. When you plug in 1 for x, them equal to each other. And yeah, you should be good. You should be able to solve for a pretty easily. You know, because you have 2 equations, 2 variables, and get b, and you're good. So, and then the textbook problems. There's a bunch of random textbook problems I assigned. Well, not random. I think it's kind of thought out, but these here, let me just show you the answers for those. Looks like these are all derivatives. Like, yeah, there's just very mechanical stuff. Like, hey, let's do the quotient rule. Let's do product rule. Let's find tangent lines. Let's find power. Let's do power rule. Let's do multiple derivatives. More tangent line stuff. Yeah. So it's all here, and I'll post these to school. I may have done so, but if not, I'll make sure I do so later today. Yeah.
Just clarifying, when a question asks for the definition of the smallest slope of the line, like what exactly is it asking for?
What question was that?
30 and 38, I think. Yeah, smallest slope of the curve.
Hold on. Was the smallest? Well, I mean, they want the lowest value of the derivative.
So does that mean like?
But I mean, it could be negative infinity. I don't know. I haven't thought of this. Oh, okay. I think I know what's going. Well, okay. Let's go to Desmos. That might be x cubed plus x. Let's do that.
Like when you graph the thing.
Let's see that. Okay, y equals. Okay, so if you look at how this graph looks, right? The derivative's never negative, never, right? So if you look at the small slope, you're probably zero could be a possibility, or something that's close to zero, right? So let's find what's the derivative here? It's gonna be 2x squared, sorry, 3x squared plus 1. So I would graph that derivative. Did you graph the derivative?
Yeah.
And what's the lowest value here?
Zero.
Well, 1. Right. So now where does that happen? Set equal to 1 and see where it happens. Happens at x equals 0. So when the question is asking, where does it happen? Is that what they're asking, right? Yeah. Well, sorry. What is the small slope? The small slope was 1. There you go. That's it.
So,
Yeah. And where does it happen at x equals 0? That's all.
If
Don't overthink it.
if the graph had a slope of like negative infinity, then the small slope would be negative infinity.
Yeah, that's just kind of weird because I don't think I would ask that because then you don't know where. What if it just keeps decreasing? Like
Yeah.
that's too hard to tell. Yeah. Like for example, if you have y equals x squared, that derives 2x. I don't know what the small slope is for 2x. I mean, I can't find a finite value.
Yeah.
It's impossible. Okay. Any other questions about this homework? No? We're good? Okay, hopefully this is pretty straightforward. All right. Let's move on to the notes. In the interest of time, I don't know if I'm gonna be able to do all these. This is a pretty lengthy. I think what I'd like to is at least get to the middle. If I get to page 4, I'll be happy. And then we'll just kind of wrap up the notes on Monday and then do because the 3.5 is actually pretty short. Oh, hold on. Yeah, 3.5 is pretty short, so I think we could do the rest of 3.4 and 3.5 Monday. All right. So let's get moving here, guys. All right, let's talk about some practical applications of the derivative. For those who are taking physics, you guys will appreciate this, okay? So just to recap, average rate change, we know what that is, right? Just slope between 2 points. If you decide to guys, quiet please. The study A and A plus H is what we use for finding derivatives. Same thing, f of A plus H minus f of A plus H minus A. But if you want to find instantaneous rate change, that gives a limiting case. So you want H, because this comes down to H when you do this fraction. You want H to approach 0. So you want this to get, you want these 2 points eventually to get close together, right? Because then instead of secant line, you get a tangent line. And what does that represent? That represents f prime of A. You be good.
So like realistically, why would we not do f of A plus H minus f of A minus H instead of like, weren't we doing like points that are equal distance from the point we're trying to see? So why would we do A minus H?
Well, I don't understand your question. I don't.
Well, we did like 5 and 6, right?
Oh, that was a table because I didn't have any other. I didn't have an equation. I mean, I don't know how else I would. I mean, that on the horn problem, number 1. Wait, 6 and 10. Yeah, because I don't have an equation. I don't know what else to do. Right.
No, I mean like if they're like the same distance from 8. So
Yeah, I mean that's just that's at that moment it's the best I can do. But if you have an equation, use the equation, of course, to get a more accurate answer. Is that I'm answering? I should understand the question. Sorry.
yeah, I mean that.
Okay. I mean, if you have a table, I don't know what you're talking about. Wait, are you talking about oh, wait, are you talking about average rate or instantaneous rate change? Maybe that's what I'm not understanding.
Yeah, what's the difference?
Limits. That's different. Oh, I don't know what you're asking. That's fair. Okay. Now that you're asking about the previous homework, I was confused. No, it's a limiting case. Because then these 2 points are actually going to be the same eventually.
Okay.
Where here, these are different points.
All right.
So. Okay, so the derivative, again, is instantaneous rate of change. Now, right, and there's a tangent line, right? Now, just so you know, instantaneous doesn't always have to deal with time, even though we deal with time often, like we deal with rates like that. But you could look at the rate of something else. Like, for example, 1, we could look at how volume changes with the radius, right? So maybe we want to find that derivative. So you don't always have to be dividing by time. Like when the radius is a particular value, how fast is the volume changing, right? And just so you know, sometimes the word instantaneous is not used all the time. If you don't see it, just assume it. Like if you're asked to find the rate of change of something, like you don't have the word instantaneous, find the rate of change of this, assume it's a derivative. If it's an average rate of change, you'll be told that. You'll be explicitly told it's average rate of change. If you just see rate of change, assume it's a derivative. So first I'll write the volume of a sphere. Hopefully you guys remember that. If you don't, here it is. Don't worry, I'm not gonna expect you guys to memorize these formulas. Don't worry about it. I mean, yes, should you know like area of a triangle and square? Yes, you should know that, but there you go, volume of sphere, right? And then you're asked to find the rate of change. So I need the derivative. So what you're gonna do is you're gonna do dv over dr. I'm gonna be more intentional when I write the derivative because I'm not doing respect to time, we're doing respect to the radius. So it's 4/3 times pi. And what's the derivative of r cubed? 3's cancel. You get that. Anyone recognize what that formula is? From geometry? Surface area. That's surface area of sphere. Yeah. And interestingly, actually, volume and area, you could derive those using the calculus. 100%. We're not there yet. Actually, you won't get there until like maybe later in the fall in BC calculus, or if you do AB, then not until the spring. But a lot of the geometry forms are derived using calculus, just so you know. And then you're asked to evaluate it. Well, that's not hard. And we have to state the units, guys. So guys, quiet, please. You're going to write like this. And also if I do the next one here. Okay, so what does this mean? These guys, quiet, please. These units, why not just put centimeters squared, right? Why put centimeter cubed over centimeters? Because we want to be very intentionally say, oh, I'm changing the volume with respect to the radius. So for every time, so the way you want to interpret this, let me write the interpretation right above. Even though you're not asked to do the interpretation, I want to do it anyway. At r equals 1 centimeter, the volume changes, or volume increases by 4 pi square centimeters each time the radius increases by 1 centimeter. That's what you want to say. If you're asked to interpret this. That's why we leave it like this here to show that, oh yeah, when this changes by 1 centimeter, this changes by 4 pi centimeters. If you think about a fraction, right? If you don't see a denominator, what do you assume is in the denominator? What number do you assume this? Exactly. So that's like saying 4 pi over 1. And it's like slope, right? What's slope? Isn't slope change y or change in x? What's your y here? Volume, right? What's your x here? Radius. So the radius increases by 1. There's a positive difference at the bottom. You have a positive difference up top, 4 pi. So really, the whole essence of calculus, if you think about it, the first semester of calculus, differential calculus, the whole essence is slope. Very simple formula, right? That's all first semester calculus is ever about, just slope, and then we just play with it. Do good.
So for the like notation, we probably centimeters cubed over centimeters, but in the right, we put centimeters squared.
No. I want this one. I don't want centimeters squared.
Oh, you said square centimeters.
Oh, sorry. I messed up. My bad. Wow. That was my apologies. Thank you, dude, for catching that. 4 pi cubic centimeters. My apologies. Sorry. Yes, the area that I should know that. Cubic centimeters. My apologies. We're okay? All right. Cool. Let's keep on moving. Now, let's talk about linear motion. So this is a lot of physics going on here. Usually we use the letter S to represent position. Position means how far you are from a certain starting point, right? So suppose S is measured in miles, fine. T in hours, fine. And you graph S versus T, fine. And you want to find the slope. Let me see what graph was in my notes from a long time ago. I don't remember. Okay, well, I'll make something up. Okay, never mind. Well, let's just say you have a funky curve like this. I don't know. I just totally made this up. Actually, let's say I do that. There we go. Okay. So what are the units for the slope? Miles per hour, right? Because think about it, you're doing the change in y over change in x, right? What's your change in y? Change in position, right? What's your change in x? Change in time, right? So you want to see how those compared with each other, right? So the slope at t equals 2 represents the instantaneous rate of changes of the position function with respect to time t. And we also call it instantaneous velocity at time t equals 2. Now the average velocity, of course, we know that, right? We know what to do with that. Average rate of change, we know what that is. But I'm more interested in this. And that right there is velocity. So velocity is a derivative. So let me write this as a text box. Velocity is the derivative of the position function with respect to time. That right there is velocity. Sorry, instantaneous velocity. Let me take it back. Because average velocity is something else. Okay, so that's what's happening there. And we're actually going to compute it. Is that repeated? Seems like it's repeated. Let me go back to my fill out notes again. Okay, I don't know what's going on. I know why that seems repeated. Anyway, so now consider the graph of velocity. Oh, here we go. Sorry, my bad. My apologies. Okay, let's say your velocity graph looks like this. Okay, I'm just going to draw the same kind of curve. Okay, now if you do velocity versus time, what are the units now, guys? Miles per what? Right. So what does the slope at 2 represent? This will represent the acceleration. That'll represent the acceleration. Because that's now the change in velocity. Yeah, go ahead.
Actually, question.
Sure, go ahead, please.
If it's miles per hour, is that velocity or speed?
Great question. We're not there yet. Just hold on to that for a moment. We'll get there. Because velocity involves velocity involves direction. That's a great question, actually. Speed. Okay, speed deals with the absolute value of velocity. Has no direction components. Velocity is what we call a vector. You haven't had those who have physics. You guys talk about vectors, right? Sophomores haven't heard about it. Maybe haven't talked about it. But let's talk about it when we get to example 2. But I'm going to explain in just a sec. So in this case, acceleration is a derivative of velocity, or it's a second derivative. So we write like this. Let me write more neatly. Sorry, guys. So acceleration, let me put as a text box here, is a derivative of velocity with respect to time, or the second derivative of position with respect to time. Yes, 100%, right. Now, velocity can be positive or negative depending on which direction you're pointing in, whatever you're considering the positive or negative direction. Speed has nothing to do with direction. It's the absolute value of velocity. That's really the key difference. So the thing is that let's say you're on El Camino and you're going 50 miles an hour and you get pulled over. Now, you could be a smart ass and say, well, no, the positive direction is going towards my house in Redwood City, but I'm going towards the other way. So I actually have a negative. So I'm not going over the speed limit. The cop will think you're a smart ass and give you a ticket. Don't use that as an excuse. But the point being is that speed, because speed is dangerous, right? Because if you get into an accident, who cares if it's positive or negative? If the velocity is positive or negative, one direction or the other, you get an accident, you're going to wreck your car and hurt somebody or hurt yourself. So it's dealing with absolute velocity, right? So speed has no direction at all. Velocity does. That's the difference.
Then, okay, that makes sense. But then how would you define position? Is that direction?
Yeah, but well, position is your change of, okay, so your change of position, that's what we're going to look at. So for example, if I'm considering this my starting point,
yeah,
and considering the positive direction, if I move this way, I have a positive change of position. If I move this way,
so
I have a positive change. Right. But you have to kind of figure out what is your reference, where are you starting from first?
Yeah.
That's what you have to figure out. Correct. Okay, so let's work on this, guys. So first off, what we need to do, guys, quiet, please. Thank you. Oh, here we go. Okay, let's take the derivative, guys. So the velocity, guys, quiet. The velocity can be written like this. That's gonna be 3t squared minus 12t plus 9. Do you want to close? You guys have allergies? You want to close the windows, or are you guys okay? You guys good? No, I can close the window if you guys have allergies. You want to close the window, or no? Okay. Oh, 12t plus 9. Sorry. Hold on. Let me do this. Sorry, that. I know you're correct. Okay, guys. We got, the more you keep talking, the slower we go here. So thank you. All right. Okay, what I'm doing right now, just to be efficient here, I decided to take the derivative of velocity and factor it because I'm probably going to need this eventually for later problems. But first off, the question is asking where's the point after 1 second. So you want s of 1, then s of 2, then s of 3, then s of 4. If I plug 1 in, I should get 0. Plug 2 in. I'm getting a little lazy now, so I'm gonna actually go to my filled out notes. Okay, 204. Okay. Is that right? Wait. After 1 second. Oh, wait, did I do 0 seconds or 1 second? Oh, I'm sorry. My apologies. Hold on. 4204. Got it. My bad. I plugged in 0. My apologies. Here we go. Cool. Okay at that?
Oh, it's a rate of possibilities.
Now, was it displacement? That's the change of position. Displacement change of position. That's s of 4 minus s of 0. So that's 4 minus 0. And that's 4 meters. So that's all it is. It's just a change of, because s of 0, remember, is 0, right? You plug in 0 into the position function, you get 0. So displacement is a change of position. And just so you know, velocity is displacement over time. So some people mistakenly divide distance by time, but that's not true. Velocity is displacement over time to get that direction component involved, right? So for example, if I walk to that room and back, my displacement 0, but then I get some steps, I burn some calories walking back and forth. Yeah. So my distance is not 0, but my displacement is 0 when I go back and forth. So that's what velocity is all about. It's all about displacement over time. Now let's look at these other problems here. Yeah, go ahead. Mhm.
With an example like walking through like pressure impact,
Mhm.
how would the equation that's account for that?
So what you do is I have to take my change in position, right? My change in position is 0. And divide by the time, 0 over anything is still 0.
Then that's not that velocity. So like the place.
So that is my velocity. Exactly. Yes, 100% would be. Yes, right. So that's what we do. So for average velocity, we do this, which is going to be 4 minus 0 over 4, or 1 meter per second. And that makes sense, right? Because if you find the slope here, what's the slope of that line, guys? 1, yeah, it's 1. But the instantaneous velocity, let's do that in green. That's much steeper, right? And what was S prime again? I already deleted. That was dumb. So it's 3t squared. Well, good, thank you. And actually, just so I don't get lazy, let me just write S prime of t as a function. So you should get 48 minus 48 plus 9, which is 9 meters per second. So it's pretty darn steep, right? Now, what's it at 2? Well, 2 is going to be negative, right? If I do that, I should have 3 times 2 squared minus 12 times 2 plus 9. What's that going to be? 4, 12, negative 3. So let me erase this stuff here. So think about what's happening. So hopefully this helps you wrap your head around this stuff. Let's say you're leaving your house, right? You leave your house, you walk away from your house, right? You walk a certain distance, you realize, oh crap, I left my cell phone. So what's happening now? You're walking back to your house. You turned around. So now, if that was a positive direction, leaving your house, going back to your house is a negative direction. That's why you have a negative velocity. Did you turn your body around? Yeah. Are you facing 180 degrees from the opposite direction, from the previous direction? Yeah. So that's why it's negative. That's why it's negative. That's why velocity. That's how it's different than speed. Is that the magnitude of velocity is the same as speed, but velocity involves direction as well. Speed is never negative; it's always positive. But velocity could be positive or negative. So does that make sense? Now, speed is 3 meters per second, though, because absolute value, right? Remember, speed is the absolute value of velocity, right? And for those who have taken physics, this all you guys have seen this, right? This is all okay, cool. So this should be pretty easy for you guys. So yeah, and velocity was what again? 3 parentheses t minus 1. And the y-intercept was 9. And if I plug 2 in, what's my vertex? -3, I think. Correct. So sketch is done. When does it change direction? At t equals 1. So basically when velocity equals 0. Because think about it. If I'm walking this way, if I want to change direction, do I have to stop? Yeah. I have to stop and then turn around, then walk again, right? So you have to stop before you change directions. That'd be physically impossible. You have to stop. And what's the velocity? 0, of course. Now acceleration, a of t is going to be 6t plus 12. Is that correct? You're right, -12, correct. So yeah, just do it. Okay, when is the particle have a velocity of 24 meters per second? Okay. Well, 24. Factor out 3. Keep going. Wait, hold on, is that right? So what does t equal here? Yeah, definitely. So it can't be -1, obviously. That'd be weird. So 5 seconds, does that make sense? Okay, cool. Yeah, I'm feeling good about our pacing here. It's good. And then when does that have an acceleration of 12? So t equals 4 seconds. Okay, all's good there? Yeah. All right. We'll see one more page here, and then we'll stop after that. Because I don't want to overwhelm you with guys with too much information. Now let's take a step back. So questions on the last example? All makes sense. Pretty simple, hopefully. Okay. Now, here you got snail. Snail's moving, right? So what always have to ask yourself, what graph am I doing? I'm doing position and velocity graph. Here's the velocity graph, right? Now think about it. When the graph's above the x-axis, the snail is moving in the positive direction, right? It's not position, this is velocity graph. When the graph's below the x-axis, the snail's moving in the negative direction. Also, if the derivative is positive, that indicates acceleration, right? Not for a position graph, what does the derivative represent the position graph? Velocity, right? While the velocity graph, the derivative represents acceleration. So you gotta be mindful about that. The snail's gonna clearly change direction at 6, and it looks like at 13, that's where it's gonna change direction. Okay. Now, if I want a speed graph, I have to make an adjustment here. If I want a speed graph, where does that go now? That portion. It's gonna look like that. So remember, as a transformation, the speed graph is an absolute value transformation of velocity graph, meaning you flip over any portion of the graph below the x-axis over the x-axis. That's what you have to do to make it to do that right. The speed graph is an absolute value transformation of the velocity graph. Flip over any portion of the graph below the x-axis over the x-axis. Not sure if you guys did that in Algebra 2 trig honors. I don't know if we talked about it in this class. I should have probably, but does that make sense? It's just a transformation. That's all you're doing. And anything that's positive stays positive because that's how value works. Okay, so hopefully we're feeling a little better about how this graph makes sense. Now let's actually go through it. And by the way, there is a question here that says, what is the maximum speed? So believe it or not, this is the maximum speed. It's actually down here, right? Even though the velocity is -9, what's the speed at -9? 9. So this actually happens at t equals 10. So the maximum speed is actually 9 meters per second. What was that? 8? What, why?
That, wait, you say you have to like stop to turn around, so we have to like stop.
So you're comparing the position again. No, again, sorry. Okay, no, you compared to position. This is a velocity graph. Yeah, it's okay. No worries.
Well, it stopped at it's definitely stopped at so yeah. All right, in the interest of time, let me actually kind of lazy here. I'll explain it. So sorry, it's a little lazy. Let me talk through while you guys are copying this down so I can make sense of all this. Actually, let me position it like this for now. Okay. I'll talk you guys through it. So we already talked about this, right? What's going on here? And by the way, velocity is positive here, still positive here, still positive here, then it's negative velocity over here, positive velocity there, right? We know this, right? So the snail starts at 0 inches per minute, inches of distance, minutes of time, right? And travels for 2 minutes steadily, right? Right, because it's going from 0 to 2. And the velocity is increasing during that time frame, right? And it gets all the way up to a speed of 4 inches. Does that make sense? Statement 1. Look at that. Statement 2 then travels for 3 minutes at a constant speed or constant velocity of 4 inches per minute. So it's still moving, but it's not accelerating, right? It's just staying kind of steady. Then it decides to slow down. So it's now it's not going as fast. Slowing down for 2 minutes until the velocity is down to 0. So it slows down. By the time it gets 7, it's at rest. It stops. So it's not moving as fast. So then the snail decides to turn around. I'm not sure you guys say snail turn around, kind of weird. But it turns around and goes back the other way. And so in this case, now it's traveling in the opposite direction for 6 minutes steadily, speeding up. So this is the weird part. This is the part where it gets weird. And this is actually kind of the whole key of this problem. Velocity is positive here, velocity is positive here, velocity is positive here, velocity is negative here, velocity is negative here, velocity is positive here, right? What's happening with acceleration? Actually, I feel bad I'm not. Oh, I'm not using the screen. So let's do it over here. Okay. So velocity is positive here, positive here, positive here, negative there, negative there, positive here. Tell me what's happening with acceleration for this the first. What's happening with acceleration here, guys? Positive, right? The acceleration is 0 because you're not changing speed. How about here? How about here? How about here? How about here? Okay, so let's think about it, and we're gonna get to this in just a little bit. But I know I'm getting a little ahead of myself. But again, we do change direction at 7. It does travel for 6 minutes in the opposite direction. We know this, right? It speeds up to 9 and then slows down eventually to 0 at 13 minutes. And at 13 it's back at rest again, right? And then finally, it definitely travels slowly increases speed, right? But let's think about what's happening here. Yes, Captain. Stop, that's all. This is being fancy. Stop. Okay, this is the big part of it when you talk. This is the big takeaway. Slowing down or speeding up. Slowing down and speeding up. I assume everyone has their license or drives a car or has driven a car or has a permit or got behind the wheel. Even if you don't have a license, I'm hopefully. So
Okay, well, even in a car, how about that? It's very important. When you brake, for example, when you're on Highway 280 and you see that cop, you know what the cop hides on 280?
Yeah.
Where's he hiding?
The exit view looks that way.
Yeah, exactly. So, well, yes, that too. That's that place. Right before the 92 interchange, you're going north on 280. There's that little hill. I think they built the hill for cops. Seriously, I've been caught there twice. And they couldn't tell myself about my opinions. But 'cause it's a downgrade, right? Because then you speed up and the cop sees you. But anyway, if I hit the brakes, I'm slowing, am I speeding or slowing down? Am I still moving forward or backwards? Still moving forwards, exactly, very important, right? So this snail is moving forward and speeding up. Sorry. It's moving forward and accelerating. That's speeding up, right? Of course, there's no change of speed here, right? The speed doesn't change. Does the speed change here? Yes. Now, because velocity is positive, so this is like hitting the brakes, right? That's like you see the cop, you're hitting the brakes, or you see a red light, you hit the brakes. But the acceleration is negative. Because these are opposite sign, are you slowing down or speeding up here? You're slowing down. Now, this is the part that's weird. Velocity and acceleration are both negative. You're going the opposite direction, but is your acceleration going the same direction? Yes, right? So the acceleration is helping you move faster, right? So what's happening in this region from 7 to 10? What's happening? Speeding or slowing down? Speeding up. It's like, think of like wind or currents. The acceleration is helping you. It's helping you go more in this direction.
Velocity and acceleration are at the same sign and you just speed up.
Got it. That's it. That said the best way you could. Perfect. Thank you. I know I'm being long-winded here, but when they're opposite each other, now the acceleration is working against you. You're slowing down, right? Because when you hit the brakes, that's inertia. That's trying to slow you down. That's friction, right? That's all the physics that's happening. That's trying to get you to stop moving, right? That's working against you. That's where you're slowing down. Speeding up, slowing down, back to speeding up again. Yes.
But you were going backwards.
Of course, but you're going backwards even more when it's negative acceleration.
Accelerate and then you decelerate and.
Right.
At the root, that's when.
Correct. Correct. So this is the big part, guys. Let me zoom in a tad. So let me clear my screen. All right, here we go. So very important. Exactly what Payne said. Speed increases when velocity and acceleration are both positive. So you're speeding up. Speed decreases when velocity and acceleration are opposite sign. You're slowing down. And then also, if you look over here, one's acceleration positive, yeah, that's what you're looking for. Slope to be positive. One's it negative, looking for the slope is negative. And very important. Speeding up. Slowing down. Make sense? We're good? Okay. I don't know if I really want to get into this today. I think we've done enough. I think I could knock this out pretty quickly on Monday. And then I want to have this as a different discussion. I think I save it for Monday. So let's stop there for today. Let's make sure the homework seems reasonable. I crossed some of these things off here, so it's really just 126 to 128 and 136 to 142, which I think you guys can handle. 1, 2, 5, 8, 9, 19. Cool. All right, you guys should be fine with the homework. So